The heartbeat of computing, mastering algorithmic efficiency through big O notation in the intricate world of computer science. Algorithms serve as the silent architects shaping our digital experiences. From sorting data in milliseconds to routing traffic across global networks, these precise sequences of instructions are omnipresent yet often unseen. The true mastery of algorithms lies not merely in their implementation but in understanding their efficiency. This brings us to big O notation, a vital tool that quantifies performance and becomes essential when comparing different approaches to problem solving. Unveiling the essence of algorithms. An algorithm is fundamentally a step-by-step procedure designed to perform calculations, process information, or automate tasks. It forms the backbone of any software application we use daily. At its core, an algorithm follows logical steps that transform input into output. These steps must be finite, unambiguous, and effective, analogous to following a recipe where every ingredient and instruction matters for the final dish. Consider a simple example: finding the largest number in an array. While humans might scan visually, computers execute predefined operations systematically according to algorithmic rules. Different problems require tailored solutions. Sorting algorithms range from bubble sort's simplicity to quicksort's sophistication, each offering distinct trade-offs between time complexity and space usage. The choice of algorithm can dramatically affect system performance, especially with growing datasets. As programmers, recognizing these differences becomes crucial for developing scalable applications. The mathematical language of performance. Understanding big O notation. Big O notation provides a mathematical framework for analyzing how the runtime of an algorithm grows relative to input size. It abstracts away constants and lower-order terms, focusing solely on dominant factors affecting scalability. This notation allows developers to compare algorithm efficiencies objectively. Instead of relying on empirical measurements, which vary based on hardware, Big O offers theoretical guarantees about worst-case scenarios. The most common complexities include O(1), constant time, O, log n, logarithmic time, O, n, linear time, and O, n superscript 2, quadratic time, each representing distinct growth patterns. For instance, an O, n algorithm processes elements proportionally to input size, while O, n superscript 2 algorithms experience exponential slowdowns with larger inputs. Selecting appropriate complexities ensures systems remain responsive even under heavy loads. Choosing between two algorithms may determine whether a website handles millions of requests smoothly or crashes during peak times. Beyond time complexity, evaluating space requirements. While time complexity measures execution speed, space complexity evaluates memory requirements. Both aspects contribute to overall algorithm efficiency and resource management considerations. A classic example appears in recursive functions versus iterative ones. Recursive implementations often consume significant stack memory due to function call overheads, whereas iterative methods typically maintain consistent memory usage. Some algorithms prioritize time over space by trading additional storage for faster computation speeds, a technique known as space-time trade-off optimization. Developers must carefully balance these dimensions depending on constraints within their project's environments, from embedded systems limited by physical memory capacity up to cloud-based platforms prioritizing rapid processing capabilities. Common algorithm categories and their applications. Algorithms fall into broad categories based on their purpose and approach. Search algorithms locate items efficiently, sort algorithms arrange data in order, and graph traversal algorithms explore relationships between nodes. Dynamic programming solves complex problems using optimal substructure properties. Greedy algorithms make locally optimum choices at each stage aiming towards globally best results, although they sometimes fail to guarantee absolute optimality. Divide and conquer strategies break down problems recursively until reaching base cases before combining partial solutions together. Quicksort exemplifies this method by partitioning arrays around pivot points repeatedly. Machine learning utilizes various types, including gradient descent for optimizing models' parameters through minimizing loss functions. Neural network architectures themselves represent sophisticated compositions of interconnected algorithmic components. Tips for effective algorithm design begin by thoroughly understanding the problem domain before attempting any solution design. Identifying key constraints helps establish realistic expectations regarding what constitutes acceptable performance levels. Prototype multiple approaches simultaneously if possible. Comparing different methodologies enables identifying strengths/weaknesses inherent within each strategy without committing resources prematurely. Use profiling tools extensively throughout development cycles rather than assuming optimizations will materialize automatically upon code completion. Leverage established libraries containing well-tested implementations whenever feasible, instead trying reinvent wheels unnecessarily consuming valuable development timelines. Implement caching mechanisms judiciously wherever beneficial. If frequently accessed data exists alongside predictable access patterns, then pre-computing outcomes could yield substantial performance improvements. Documenting decisions made during selection phases improves long-term maintainability since future contributors benefit from clear rationales explaining why particular techniques were chosen over alternatives available at given junctures. Practical examples illustrating concepts. Let's analyze 3 fundamental searching techniques, contrasting them against typical scenarios where they'd be applied appropriately. Linear search iteratively examines list entries sequentially until target item found or end reached. Suitable small collections where frequent updates expected. Binary search requires sorted dataset partitions midpoint, iteratively narrowing search window, exponentially reducing potential matches per iteration. Ideal. Ordered structures needing efficient lookups. Hash tables maps keys to values via hash functions, facilitating near-instantaneous retrievals regardless of collection size, provided good distribution ensured among buckets created by hashing mechanism itself. Each presents unique advantages matching specific contexts. One wouldn't implement binary search on unordered lists nor expect hash tables delivering reliable ordering characteristics required by certain business logic constraints. Now examining basic sorting routines, highlighting differences between approaches. Bubble sort repeatedly swaps adjacent elements, moving largest values toward right side, progressively refining order though inefficiently for large datasets. Merge sort divides array recursively into halves, sorts independently, then merges back, maintaining stable ordering throughout entire operation, consistently providing O(n log n) performance. Quick sort selects random pivots, partitioning arrays accordingly. Achieving average case. Similar merge sort, however susceptible worst case degenerations, requiring careful pivot selections to mitigate risks. Effectively choosing between these depends heavily upon particular situation. Bubble sort useful educational purposes, demonstrating fundamentals, whereas merge sort preferred critical systems demanding guaranteed upper bounds regardless external conditions. Advanced topics. Recurrence relations and amortization analysis. Recurrence relations mathematically model divide and conquer algorithms by expressing T n equals a asterisk T n/b plus f n, enabling derivation of closed-form expressions predicting asymptotic behavior accurately. Solving recurrences involves techniques like substitution method, recursion tree analysis, and master theorem application, all instrumental for assessing algorithm behaviors analytically. Instead, empirically testing alone proves insufficient guidance, making sound architectural decisions reliably. Amortized analysis considers average case performance across sequence of operations rather than individual event isolation, particularly relevant when dealing with dynamic data structures undergoing frequent modifications where occasional expensive actions balanced out cheaper regular ones, leading overall better throughput rates. Achievable practically viable options. Real-world deployment scenarios. This concept shines brightly in implementing advanced queue variants such as dequeues, allowing both ends insertions/removals efficiently by distributing costs evenly across successive invocations, ensuring no single call dominating total expenditure, disproportionately skewing perceived effectiveness, unfairly misrepresenting actual capabilities. Possessed inherently robust underlying designs engineered precisely address those challenges proactively ahead potential bottlenecks arising naturally. Course normal operation cycles encountered routinely production settings. Evaluating real-world impact through case studies. Consider Google's PageRank algorithm. the cornerstone of its search engine dominance. By applying matrix multiplication principles to web page link graphs, this elegant solution ranks documents based on authority derived from other pages referencing them. Despite its apparent elegance, naive implementations struggled with computational intensity. Optimization efforts focused on sparse matrices representation coupled with power iteration methodology significantly reduced resource consumption, enabling scaling billions web page references seamlessly manageable infrastructure capabilities. Modern distributed computing frameworks provide today. Similarly, ride-sharing platforms rely on optimized pathfinding algorithms balancing route distances against driver availability factors, dynamically adjusting matching algorithms, continuously evolving city landscapes, traffic fluctuations, ensuring timely pickups, drop-offs experienced consistently high satisfaction ratings. Customers appreciate reliability, convenience, promised service levels maintained, consistently competitive edge market spaces dominated rapidly changing technological paradigms. Challenge innovation, perpetual improvement, imperative sustaining relevance amidst relentless progress, sweeping industries constantly forward momentum, industry-wide evolution trajectories followed relentlessly across sectors alike. These examples demonstrate how theoretical understandings translate concretely impactful innovations, transforming abstract concepts, tangible benefits. Society regularly interacts, relies upon daily lives profoundly influenced positively. Negative manner according knowledge employed responsibly, ethically, conscientiously guided, mindful consideration, implications born thereof, decisions made shaping futures collectively. Conclusion: mastering algorithm efficiency through Big O notation empowers developers to build scalable, high-performance systems capable of handling ever-growing demands without sacrificing responsiveness or user experience. To advance your skills further, actively engage with coding challenges on reputable platforms like LeetCode or HackerRank. Apply what you've learned here by analyzing time and space complexities in practical scenarios, continually refining your ability to optimize solutions efficiently.